Okay. Let's go, guys. All right. Faraday's law. To understand, guys, quiet. To understand Faraday's law, you have to understand magnetic flux. And let's get that down real quickly. And first, you'll have questions, but the questions you'll have will not matter in the long run, and you'll see why. First, let's do flux. This is big phi, uppercase, or lowercase, either one, a little m here. And some people do another subscript on that. They do, I can't remember, it doesn't matter. But anyway, this is flux. And this equals BA cosine of theta. And I'll just do it all down here. That's the lowercase phi, which I generally write when I'm in a hurry, okay? And that, I'll just write that's your magnetic flux. You get in a hurry.
We should have done relativity.
Well, I would like to do it, just don't have time.
Well, then do it instead of like lenses and stuff. But I guess that's what you need for APs.
That's the problem. And flux is in Justin, what's flux? It's not Henry's. That's inductance. What's flux? What's he used for?
Weber's.
Weber's.
What? How do you know that?
I was here.
Oh, you guys did this already?
Yeah.
Oh, I didn't know that.
There you go, guys. Weber's or Weber's, whatever it is.
Oh my God.
And B is the. Here's what you have.
Weber's.
Before I do anything else, let me draw this. Here's some area. You know, that's just your area right here, okay? And the B field's going through that, let's say, okay? In other words, it's just like, instead of being solid, it's just an area. And the B field's going through it, okay?
Yeah.
Okay, so where you get flux through the stuff, well, that's what's going on. But
That's supposed to be three-dimensional?
Yes.
Okay, I can see it.
Yeah.
So
here is your areas like this. And the B field going through your area, okay?
Okay.
Just geometric area.
The big phi is the same thing as magnetic flux?
Well, yes. They're the same thing. And so and that's in Weber's, and then B is the B field through your area, magnetic field.
That doesn't seem that way. Tonight I'm going to watch all the fluid.
That's what I was going to do too. I have to do English stuff first though.
What? English?
I was going to do multiple choice. What? We only did one.
Wow. You've done a lot of them. You've done like 4 or 5.
No.
Not full ones, but...
My whole class
actually do
my whole class did on 3 ones.
Like I said before.
The ones I did on my own, I did fine with. I still want to remind you.
I'm like, I'm going to assume I did good enough on the practice one to do good.
She said I got an 8 on my statistics.
I never asked you.
All right, guys, now pay attention to this. It says the angle between B and A. And that's always tricky at first because if you ever thought about the direction of the area, it is the direction perpendicular to the face. Okay? So if the area is that way, that's the direction. Now let's say B feels that way and the area is that way. This is the angle between the two. Everybody clear? And I'll draw it up here just in case you do, but keep writing that.
So we do this a lot in physics C?
Some, more than in B, and you do a little bit of calculus along with it, but it's not that hard. I mean, and you guys are going to use an equation that they have to derive every time. I don't know why. I'm going to keep writing that, guys. Here's a simple example. Here, let's say this is your area. 3D, areas like this. And the B field is that direction. Furthermore, the area is also that direction if I drew it correctly, right? In other words, if the face of the area is perpendicular to the B field, then the area and the B field are the same direction by this definition.
So the degree is 0?
Yeah.
So what is that?
In that case, this theta would equal 0, okay? So you have the most flux when your B and A are parallel.
So
right?
0 flux means, wait.
No, you have the most flux when B and A are parallel. In other words, when they're perpendicular. You follow me?
Yeah.
Because the area of this sheet of paper is that way. If your B is that way, okay? Now, but let's say that it's not quite like that, it's this. Let's say your area is like this, and I'll draw a 3D thing here again. The area is that way and your B is that way. Well, in that case then, your theta is going to be, let's see, this right here, okay? You always choose a small sign between your B and A when you're doing the cosine of theta, okay?
The arrow is your B, right?
Yes, yes. This is B. So in this case, B is that way, area is that way, right?
Yeah.
Well, you can use that angle there too.
Those are really good 3D things.
Well, thank you ever so much. I may major in art, you never know. All right, so in other words, so if you say B times area times cosine of theta, that's the flux through that area. Now let me show you this conceptually to make sure you get it.
Wait, what is theta that top one?
Either one, they're both the same thing. It doesn't look like it, but they are. Let me erase one of them, okay?
Yeah.
All right. No, it's not either or. It's that one right there. You're right. It is that one. Okay. In about another 3 or 4 minutes, you'll be, Prath making Ashka for us initially. I know Ashka has. Now, next year is either I want to do IB and C or APB and C, but not both. It's just, it's too weird, you know what I mean? I don't cover either one well enough. Okay, so here you go. So let's say the B field's that way. And I turn the area, and let's say the area is due to a coil. You with me? So there's a piece of wire around this edge here, and that's really the area of that coil. It can be a square coil, it can be a round coil, whatever, it doesn't matter. But I turn that coil like that. Now there's no B field lines through it, is there? Therefore, there is no flux through it. So I went from full flux to none. All right, now you have to do that, no, but that's an example. Okay. And, okay, that's got it. Now, so everybody understands flux and how it can change, give me another way, I asked you all 3 ways in which you can change the flux. The one is change the angle, right? What if I make the B field less? Then the flux gets less, doesn't it? Because BA cosine theta is going to be less. What if I stretch the coil? It gets bigger, doesn't it? I change the flux. Now you say, well, how can you really make the area smaller? Here's a simple example. Let's say I have a B field into the page, a magnetic field into the page. And let's say I have a system like this where this is a wire, and here's a bar that floats on that wire, okay? Or at least runs on the wire. And if I pull that bar this way, I made the area, because here is where the coil is. This is where the coil is, right? So that's my area. Makes sense? And BA cosine theta. If I pull that bar this way, I just made the area bigger, didn't I? Yeah. So therefore, the area can get bigger just by a simple example of this kind of stuff. Okay. All right, with that in mind now let's do Faraday's law. Now you understand what flux is.
What is flux?
Mathematically, it is the B field through the coil times the area of the coil times the angle between the area and the B field.
What is it
So it's
mathematically?
Oh, you mean what's conceptually?
Yes.
Don't know, don't care.
Okay.
Well, I will tell you this. Haldane Resnick goes this whole thing about it's the flow, blah, blah, and it's all true. But you don't need to go into it. It's just BA cosine, it's the flux. Can you handle just a mathematical thing when we call that the flux?
Yeah.
It's an amount, and that's all you need to know.
That's all we need, so that's...
But I will say this. Whenever I went like that, the flux went to 0, didn't it?
Yeah.
Because theta was 90 degrees, correct?
Yeah.
Yes.
But that's mathematically why it's 0. Conceptually why it's 0 is because when you turn it like that, there are no B field lines through this coil anymore, are there? Because they're this way. And the face is that way, right? So in that sense, that's a conceptual definition as well.
That actually makes sense.
You with me?
Yeah.
All right. Okay. And now, here's Faraday's law.
What that was, what is that?
That was magnetic flux.
It's going to be voltage, and they do this. Some books write this, and some leave the N on. I'll leave the N in there, and it's going to be delta V.
Can't we just do V instead of E?
That's the way every book will do it this way. But if you want to put V in your notes, I don't care.
Why do they have to be so many names for?
Voltage?
Yes.
I don't know.
They hate us.
The delta T is just over the delta P, right?
Yeah.
Oh.
Yeah, because the number of coils will not change.
Now I kind of really hope there's a free response over Faraday's law because it'll be easy since it's so fresh.
Yeah, well.
That's true.
And if you do enough applications of Faraday's law, it's very easy.
How often are they doing? Because I've only seen like one. It was 2005.
Oh,
or
there'll be
2000.
like the multiple choice. You know
It's been
what?
one in
Let me do
almost
some more.
everything that I've done.
Are they on the really?
Yeah.
Have you done them or just skipped them?
No, I've done some of them. I did the older ones, but I skipped the newer ones because I knew we were going to go over it. So I figured that way I actually had to do
I
them.
don't know how to do
It's like 1999 to 2003. There was one number two.
Yeah. I've done like 2005 to 2008, and I haven't seen
I didn't hear my printer printing, and I knew it was because the thing, one outside the margins thing came, and now they're printing. Because I want you guys to have this before you get out of here.
Yeah.
All right, now this says the voltage in that loop. Because really, what we're talking, it's not really a book here, is it? It's a wire on the edge of the book. And I could just easily do this. Let's say we had a wire on the edge of the wheel. You with me? It's the area of the wire, enclosed by the wire. All right, okay? So that's what we're talking about here. This says, and I go back to this because it's lighter. So this is, if I change the flux, there will be a voltage in that wire. And it'll produce either current this way or that way, depending on how I turn it. Okay? So if I do this, that meant as I was turning, I changed the flux, didn't I? As I changed the flux, there was a voltage in the wire, producing a current. Okay? And this says if you have 5 turns, 5 times the voltage. Make sense?
5 what?
You have five loops. Notice if I have 1, 2, 3, 4, 5 turns of
Is that
wire.
what the end is?
That's what the end is.
That's energy.
Yeah. Now let me put all. Well, let me give you your definition. But
Did you
yes.
list this law?
Huh?
On the equation sheet, is this on there?
Well, this Faraday's law, Lenz's law, tells you what direction the current will be.
Okay, so we have to know this, like memorize it.
Yeah.
Okay.
Yeah, but it's not hard.
Yeah.
Okay, let's do this. First one, this is the voltage produced in the loops, our loop, depending on how many there are.
So much physics in like a week.
Yeah, dude. This is more than I did all last year.
Yeah.
So that's the voltage produced, and N is the number of turns, our number of loops of wire.
Why is it negative?
It has to do with, it's a conceptual thing. Lenz's law, you'll see one in a minute. Number of turns.
What are the number of loops?
Oh, whatever you say. Our loops.
I feel like the hardest thing we do is electricity because there's just like so much stuff with it.
Well, but the cool stuff is with electricity because it's almost like magic, produced by stuff you really can't see.
Forces are the easiest thing ever.
Yes.
Last year,
Yeah, let's
electricity
see.
was interesting. Unless you put springs in it. It's not that, but it'll confuse you.
Now, guys, can you all, what is that?
What do you mean?
It's just the change in flux with respect to time. Do I need to write that?
No.
Good.
I'm gonna write.
So change in flux.
The change in flux with respect to time. I could do the change in with respect,
So it'd be Webers per second.
yeah, which is also voltage.
It is voltage?
Well, yeah.
Oh, huh. Weird.
I guess it'd be Webers per second, but it's really are just voltage. I never thought about that, but it is voltage. Okay. Now, I could also, we said that this is true. But this equals this, if you just put in all the details. Right?
Yeah.
And here's the deal. We'll write that down, and we'll tell you that, and then we'll do some problems with Faraday's law. And then we'll get the direction real quick after we do one or two problems with this.
I don't think I ever did that one worksheet.
On the fluids?
Yeah.
No,
Well, I'm probably sure you did.
not fluids, over.
Energy degradation.
Yeah, some global warming.
You should have. It was probably on the test somewhere.
Oh, that one that we. Yeah.
Do like,
Well, that one I counted for a grade, didn't I?
yeah.
I still have mine, I did it.
Yeah, I'll take them.
I'll give it to you sometime.
I turned mine in.
I'm not gonna be in this. Well, I guess I'll be in this class Monday. Can I not do it?
No, I need grades.
I'll be studying.
I
Can I give it to you like
can't.
after all these tests?
I'll take it then.
Okay.
All right, guys, but here's the deal. Let's say your B is changed, but nothing else is changing, okay? Then this would equal this. Whatever is not changing comes outside the delta. Does that make sense?
Yeah.
So I'm just going to do, for instance, if, I say if, and I don't want to do all three of them because I don't have time, but let's say if the B is not changing. And I hate writing like this. If B is not changing, then this becomes this. And let's say the theta is not changing either. Well, whatever is changing, guys, has got to be within the delta. You follow me? But whatever's not changing comes outside. You with me? It doesn't go away, it just comes outside the delta. Just like a derivative. And I could just easily do, let's do this, B and theta. B and theta are not changing. I'll pull both of them outside because that would make more sense. Because usually just one is changing.
So then just B would be getting bigger?
Yeah, or getting smaller as the case may be. I'm going to do this.
I'm just going to accept this as like a fact.
All right. That's one example. Here's another example. And the third example is where theta changes and the other two come outside, okay? And whatever problem that you have, it'll be one of those three.
What if none of them change?
Then you don't have a change in the flux, therefore you don't have any voltage. Right? Because either B, A, or cosine of theta has to change. All right. You know, the weird thing is, well, I would think that's probably a nonsensical question. Tons of kids watch this thing. That was my question. You know?
I mean, I was kind of joking.
Oh, no.
I knew that it wouldn't have any.
Oh, seriously? Good.
Yeah.
Good. Because I'm thinking, that's a stupid question.
Yeah.
But I didn't say that. But if you're thinking that question, it's a great question.
I hope people watch this video.
Oh, don't want to put that on YouTube, do I?
No.
Yeah, why do Mr. Brown?
Yeah, you do.
Okay, now let's do some example problems. Guys, get a white book.
Yes, actually, yes. You can have this. What do you want? What is this? Is this like an IB physics book, or is this the physics C book?
I found out 2 days ago if they actually had physics.
I made a walk. I don't know. So there was one that
I think it's chapter 19. Guys, no. Chapter, keep going.
I feel like I'm going to do bad.
History's not these stereotypes, and it's my hardest.
Oh, I love history. But I feel like I'm going to do bad. I don't know enough about this history. Do it.
Okay.
Any history class?
Guys, and I want to show you something that usually I'll forget to tell kids this, and it's a good example. And turn to page 590, and they show you a very good example there. And I'll put it up here as we talk about it. It's the one on the bottom. It has where you have a magnet you're going to bring closer to a coil. And I think, yeah, that's what's going on here, okay? Just a second. Oh, they do it a different way. It doesn't matter. What they have a magnet right here, correct? And they pull